On December 15th, 2023, I opened up the Desmos graphing calculator, this thing, and I started typing. 1 month later, I arrived at this. Everything you're looking at right now is made entirely out of math expressions. A being of math made with math. This was the result of well over 50 hours of work using all the knowledge gained from my 3 years of making Desmos graphs. So, how do we get here? Most of the graph is made out of two different kinds of functions, parametrics and polygons. Polygons are made using points. Desmos has a built-in polygon function, so by plugging in a few points to act as vertices, it will connect the lines for you and fill it in. For parametrics, imagine putting a point down and then adding a variable to the coordinates. As you change the variable, the point moves. A parametric function is essentially doing that, but drawing the trail that the point makes. If it forms a closed figure, you can also fill in the inside of it, so you can make shapes as well as lines. Generally, parametrics are much more useful for curved designs, while polygons are better for jagged edges. Polygons are also much more resource efficient than parametrics, making the graph run faster. So with both of these put together, I was able to make a lot of shapes and designs. Another thing to point out is the colors. When you load up a graph in Desmos, you normally only have 6 colors to choose from. As you can see here, there are a bit more than 6 colors in the final piece. So where do these come from? As it turns out, you can make custom colors yourself. If you type a new variable and set it equal to an HSV or RGB function, you're then able to use the color in any expression. Alright, actual math time. Before I even started parts of it, there were some tools I wanted to make that would help me create things. These include animation variable, circle, square, rotation of any points, stretching of any points, flipping points across the y-axis, star shape, 3-point Bezier curves, 4-point Bezier curves, universal identical line thickness across multiple different divides using the width of the screen, and finally, a function to graph 3D perspective in 2D space. Okay, I should probably actually explain that last one. So you know how the further away an object is, the smaller it looks? All this does is basically take a point in 2D and scale it by how far away it is from the camera. The higher the value of z, the smaller it becomes, and vice versa. This thing at the end makes it so that an object stops being drawn if it goes behind the camera, where z is negative. Oh yeah, I also made an entire function for rotating things in 3D, but then just ended up not using it. So that's cool. But with that out of the way, let's finally get into how I actually made this thing. For the background, I started with a solid purple color. Then I got a square polygon and stretched it horizontally to cover the screen. I shifted it up a little so now I can scale up the height while the bottom part stays still. I incorporated lists of polygons, each with different heights, to create several different scaled versions with a single expression. Hold on, let me back up for a minute. This thing with the brackets is a list. It can also be written like this, or even like this. Whenever you use a list in an expression, every number in it is run through it separately. In other words, lists let you graph hundreds or even thousands of lines with one equation. You can probably see how this would be useful. Lists can be made up of pretty much any kind of element, be it numbers, points, polygons, and even colors. They're pretty much the main reason I was able to make this graph in under 300 expressions. Anyway, back to the video. Then I moved it to the bottom of the screen, lowered the opacity, and set the color to a light orange. And after all that, we got a gradient. This gradient technique is used a lot in the graph where things are overlapped with different sizes and set to a low opacity. For the mountains, I made a line of points going across the screen. Then I used the random function, which creates numbers between 0 and 1. For each of the 57 points, they're all raised up a random amount to create jagged edges. After putting 2 points in the far left and right corners, I made them into a polygon. The blurring effect on the tops of them were made in a similar way to how the gradient was made. Now some stars. With the random function again, I scattered a bunch of points across the screen and also randomized the size of them. Then I duplicated them and made them bigger to give it a slight glow. The planets were one of the few things that weren't made with points, polygons, or parametrics. The lighting for them uses implicit functions, basically the standard x and y equations that most people probably use Desmos for. In this case, I took the equation for a circle, filled the inside of it, and then used another circle to cut it and make a crescent moon shape. Then with the gradient strat, I could create pretty realistic looking lighting using lists, along with outer glow that was made with outlines. Figuring out the direction that the gradient should go was actually a bigger issue than I would have expected. See, I could have just eyeballed it and done it manually, but instead I decided to make the lighting automatic. which resulted in a function that used the planet's size and location in comparison to the center of the screen in order to make it. And then I decided to graph each planet using one line instead of putting them as separate expressions. So now the whole thing looks like this. Unit circle background. It looks pretty straightforward at first, but there's a pretty interesting method I used for it, namely the straight lines. When you make a line by connecting points, like in a polygon, you can't normally split the line anywhere without just making a new set entirely. However, if you include a point with an undefined number, Desmos can't actually graph it. So instead, it just breaks it where the point would have been and lets you make multiple disconnected lines with one expression. Using that, I was able to graph all of the straight lines in one expression. Other than that and some added glow, the rest isn't too bad. For the design around the circle made out of thin lines, it consists of all of the shapes from a triangle to an octagon stacked on top of each other. The black hole is also pretty simple. It's made out of 5 sets of circles that use the gradient effect from earlier. It consists of the black center, the white outline around it, yellow aura, orange glow, and then one final orange highlight that's a bit less noticeable than the others. I used a really dense sine wave on the highlight's radius in order to make a hazy cloud effect, and I made the black center pulse with the animation variable in a sine wave. For the flower petals, I used rose curves. Rose curves are based on polar functions, which involve an entirely different coordinate system, but to put it simply, take a sine wave and wrap it around a circle. The lemniscate infinity sign is pretty similar to the rose curves, but instead of a sine wave, it's the square root of a cosine wave. The vines on the signs were made from 2 slanted sine waves put together, which involves combining the 2 in lists and making them indexed based on t. The lines were shifted over, rotated to stick out under the flower body, and resized and repositioned to give some variance. I also gave them a slight curve by making t affect the rotation as well, so they look more like they're spreading outward. Now the eye. Hey, remember that star shape I showed for half a second earlier in the tools part of the video? Here's where that's used. Behind the eye, there's a black circle glow in 2 star-shaped areas. The eye shape was made with 2 combined quadratic functions, then the pupil was made with a compressed circle. The 1 and -1 to the sides use the same line break method that the lines on the unit circle used. In terms of raw data, the math runes are the largest part of the entire graph. It's so massive I had to create a separate folder to store the points for them. This is also where Bezier curves finally get to shine. Bezier curves are curves that use points to determine their trajectory. If you've ever used the pen tool in something like Photoshop, that uses a Bezier curve. So first, I created the circles for the runes to go in, along with a large black bar for shading. Then I had to make the symbols themselves. I first took a screenshot of the symbols as they appear in Desmos, and then inserted the image to trace over them. Here's my method for doing so. First, create an empty table and fill it with a bunch of points. The actual numbers don't matter, and they can all be the same point. Then, using that table, make a Bezier curve like this. Make sure the upper bound of t is a pretty high number as well, to about 1/3 of how many points are in the table. The result will be a series of curves that travel from the first point in the table to the last point. Now set the table to drag in the settings and start dragging the points around. You can now essentially draw with Bezier curves and trace over the symbols in the pictures by hand. What, you didn't think I used a program or something to trace them for me, did you? Doing all of them took me a couple of hours, but it was much better than having to type the numbers in manually. After that, it was just a matter of getting them to fill properly, which just involved making sure that the last point in the table was near the first one to form a closed loop. I also added a bright white gradient across the bottom of the screen, which blended with the runes in a way that made them shine really nicely. The arms were made in a similar way. Just for the record, I usually don't like going too overboard with tracing things. When I do, I generally try to either make the reference images myself or take them from things that aren't owned by anyone and are easily accessible, like the math symbols. In this case, I used a picture of my own arm. One thing you may notice is that the hands have 6 fingers each. Now me personally, I don't have 6 fingers on one hand. This just meant I had to make some small adjustments and move a few fingers around to make room for the 6th one. The lighting was done by making a copy of the outlines and scaling them a bit. Now we get to the wings. This was the first thing I made in this graph. It's also the most complicated part. The wings can be broken down into 5 steps. 1. Trace out the integral symbols with Bezier curves. 2. Create the basic skeleton for the wing shape. 3. Use the wing shape to position the integral symbols. 4. Rotate and resize them accordingly. And 5. Flip it for the other side and create the flapping animation for them both. So first I had to trace the symbol. Since integrals are symmetric, I only traced 1/2 and then flipped it. To make the skeleton, I used 4 large curves that spread outward to act as the rings. I don't know wing anatomy, I think these are called primaries and secondaries? I'll just call them rings. Then I took the curves and broke them up into points which act as the positions for the integrals. The rotation and sizes for each integral on the rings were scaled linearly. Each ring has the same pattern of rotation, while the sizes use the same pattern with different scales. Then I positioned the wing into place, rotated it a little, and then flipped it for the other one. The flapping was done by rotating it with a sine wave animation. Then I made a color that circles through the rainbow, put them on another copy, and scaled them up a little to give it that rainbow trail effect. Then more glow, and that's it. Now this may not sound too bad compared to everything else. The real thing that gave me trouble with this is how many things I had to put within other things. The full set is composed of 2 full wings, which are each made out of 3 copies of the wing shape plus glow, which are each made out of 4 rings, which are each made out of 20 integrals, which are each made out of 7 Bezier curves, which are each made out of 4 points. By the way, you can't put lists inside other lists. I used one expression for each wing shape. That is 1,760 points. This involved a bunch of expressions and a bit of black magic to work, but the simplified version is that I made each integral symbol into one list element and then graphed all 84 of them at a time. Why didn't you just use multiple expressions instead of doing everything on one line, I hear you ask? So anyway, the floating rocks. In the beginning I talked about how I made a function to graph points in 3D. Here's where it really came in handy. Each of the rocks are triangles. I started by just generating one of the points for each of them. To do this, I mapped a circle onto 3D that went around where the boss was and then took points along the circle at random values. I also randomized how far away they were and their vertical position. I put the ones in front of the boss into one group so I could layer them accordingly, while the others were layered behind. Then just take the points, offset them a little, take the points, offset them again, and you got triangles. Take those triangles, shrink them a bit, and you got lighting. Here's a detail you may not have noticed. There's an orange lens flare in front of the right wing. It's a pretty small detail, being made out of a bunch of points that are scaled up a ton and set to a low opacity. I didn't feel like making an entirely separate section for this, so it's lumped in with the rock shards. And for the final part of the graph, the foreground cliffs. They were made in a similar way to the rocks in that they used a circle in 3D with the distance randomized for the points of them. The cliff faces were done manually, and then the lighting was from scaling up the cliffs, as well as scaling them down for this cool blur effect. Since it's done manually, that does mean that the whole thing breaks if you randomize the points again, but for once, I didn't care enough to do it the hard way. The very last detail of the graph is my signature, which was once again made with Bezier curves. Fun fact, I didn't use cursive font because it looked nice, it was actually because I didn't feel like using a lot of points and lines to create block letters. With cursive, I only had to use 3 lines to write everything. And that's everything. The whole thing is done, and psych, we gotta optimize this thing. It runs terribly at the moment, and we need a way to make it go faster. So I may have lied to you a little bit. I mentioned before how some parts of the graph were parametrics and some polygons. The truth is, pretty much all of the parametrics I used ended up getting turned to polygons to make it run faster. The polygons aren't the best for curves, so I was sacrificing image quality for performance. So I decided to make it controllable. I made a slider that controls how many points are used for polygons. Lower values, more jagged edges, less points drawn, runs faster. If your device can handle it, then you can turn up the slider for maximum graphics. But even then it's still slow. We need something else. Luckily, I had just the thing. You can import images into graphs, but you can also move them around and animate them just as you could with points. Images don't require hundreds of calculations to create, making them really quick to load. If I were to make a setting that replaces parts of the graphs with images of them, the whole thing would run much faster. So I replaced every moving part of the graph with PNGs using a website called Desmos V. I overlaid them onto the originals, and hey, when everything else is turned off, it runs really fast. Key point, when they're turned off. How do you turn off parts of the graph with a slider? Making them invisible doesn't work, using something like a piecewise or undefined value still calculates everything, so that doesn't work, and we don't want to have people just manually turn off all the folders. Here's your answer. We do this. If an expression has an error in it, it stops trying to be rendered entirely, giving back all our precious frames. Alright, cool. The next question is, how the heck do you cause an error only when a slider is at a certain value? If you have a list with ellipses, it fills in the numbers between each value automatically. So for example, something like this would make a list with the numbers from 1 to 10. Normally each number only goes up in increments of 1, but you can change the step size by doing something like this. You also don't need to use one value for this, you can have 2 of them. But here's the thing. If these two numbers don't have the same step size, the whole thing implodes on itself. So here's the switch that breaks everything. We have this value be controlled by the slider for the image mode setting. When it's off, at 0, everything runs just fine. But as soon as we turn it on, everything errors out and the images replace them. Now we can see the full animation without running at 5 frames a second. Naturally, I didn't leave this setting as the default since it kind of goes against the whole point of using Desmos when it's all just images instead of expressions. I still left it for people who wanted to see everything without needing a super fast computer though. And that just about does it, for real this time. That's how I made the final boss of math. I hope you enjoyed my ramblings. If you did enjoy it, feel free to give it a like. Oh yeah, by the way, what is this? When I posted that video, I had no idea it would get that much support. Just wanted to say thanks for that. It's honestly surreal to see it get that much attention. Anyway, thanks for taking the time to watch this video. It took quite a bit of time to make. In the future, I'll probably make videos that go more in-depth about the specific expressions and why things work the way they do in graphs. I figured that this video probably wouldn't be the best place to start out with that kind of thing, so I tried to keep it as concise as possible. With all that said, glad you made it to the end, and I'll see you later.